IT team, am I audible to you clearly?
Yes, ma'am. Yes, ma'am. You are audible.
Yeah. Is the screen also visible to all of you?
Yes, ma'am. Yes, ma'am.
All right. A warm welcome to all the participants for today's session. Welcome to this session on deep learning, YOLOV3 and its applications on behalf of Aegis School of Data Science. My name is Nada Parkar and I'll be your host for the evening. So today we have with us our proud alumni, Mr. Karan Samani, who's currently working as a product manager, AI ML Tata Communications Transformation Services, that is TCTS. Uh, Also, he has a great experience in this field of AI, ML, deep learning models. He's previously worked with Capgemini for 6 years as a data scientist, and he has more than 7 years experience in the IT industry and worked on various algorithms of machine learning, deep learning, and computer vision technologies. He has done his post-graduation from Aegis School of Data Science, and he's also done his, prior to the post-graduation, he's a bachelor in BSc and has done his master's in computer science from RD National College in the year 2017 to 2019. So he's here with a very amazing application of deep learning, that is YOLOV3. It is a object detection algorithm, and I will not talk much about it. Over to you, Karan. So you can take ahead the session from here.
Okay. Hey, hi. Good evening, everyone. So I'm very glad to attend this lecture, give this lecture on YOLOV3. So I remember somewhere around 2 to 3 years ago. So I was attending this kind of lectures as well through Aegis. I already had the experience in data science, but I wanted a kind of a degree so that there will be some kind of degree with me for the data science course, and Aegis gave me that opportunity, and I also attended these kind of lectures. Now I'm very glad to conduct these one of these kind of lectures, to teach the the next generation about data science and machine learning that is going to that is happening here in this era. Can you see me? Is my video visible?
Yes, Karan, it is.
Yeah. Okay. So I'll not take much time. So my introduction is already done. So I'll just directly go ahead with my presentation and with talking about a little more about deep learning and YOLOV3. Okay. So let me just share my screen. Yeah. Let me know if it is visible once.
Yes, your screen is visible.
Oh, okay. Yeah. So today I'm going to talk, give you an introduction about deep learning and a little, I'll touch a topic of YOLOV3. I know some of you are not very well versed with deep learning, as well as they have not started their deep learning course as well. Or some of you, they have started their deep learning course, but they don't know very deep knowledge about it, and they don't even know what is YOLO. Of course, so you are at a learning curve right now. So what I'll do is basically I'll first introduce you with some building blocks of deep learning. So what is the concept of deep learning and what all things involved in that? And moving on forward, I will just touch a topic about touch the concept about YOLOV3, and I'll also introduce you with one of the use cases which me and my team in Tata Communications, they applied like a few months back, like a real life example. And I'll just give you a kind of an introduction about it, and I'll just tell you what YOLO and what deep learning can do in real life problems and your real life use cases. Okay, so let me go ahead. Okay, so let me just start with basically what is deep learning. Okay, so for starting with deep learning, so deep learning is kind of comes under an umbrella of artificial intelligence. So if you guys know what is artificial intelligence, it can be any technique that enables computer to mimic a human behavior. So anything. So if you have heard about robotic process automation, so it is something like you have some kind of a drag and drop. You have a tool wherein you can drag and drop a lot of things. You can drag and drop a lot of gestures in that tool, and you can, for example, give an instruction within that tool that go to Google and search for some cats and dogs images. But you do this via automation, right? So these kind of things also mimic human behavior, right? So you can say in turn it is a part of artificial intelligence, and it is an intelligence which comes artificially. Artificially is in something which is man-made is known as artificial. There are artificial lakes and artificial dams and all those things. So the intelligence which comes from man-made is something known as artificial intelligence, which mimics human behavior. Okay. So within this artificial intelligence, there is machine learning. So as you guys, you are in this course, data science, you might know that machine learning is nothing but an ability to learn, ability of a machine or ability of a computer to learn without explicitly being programmed. Okay. So for example, you have been given an input and you have been given an output. So you just ask the computer that this is my input, this is my output. I want to learn my machine so that every time whenever I give this kind of output, my machine should give me this kind of input. A output, A input, B output. Okay. So you don't program it explicitly. You don't have if else ladders. You don't have cases and all those things. The machine learns it by itself. You just give the data and you just build a framework over it. So that is what machine learning is. Okay. Within machine learning, there comes a concept known as deep learning. So why is deep learning like within machine learning, or else it is not kind of a artificial intelligence and machine learning and deep learning, all these are different concepts. And why deep learning is one of the different concepts and it is within this umbrella is deep learning extracts the patterns, okay, and from the data, and it uses neural networks. Okay. Machine learning, as you guys know, may be knowing that machine learning does not mean that it works with neural networks. It has various other techniques like linear regression, logistic regression, ensemble techniques, bagging, boosting, all those things. But yeah, if we deal with neural networks and we try to detect some kind of patterns in our data, so that concept is what deep learning is basically. Okay. Okay. So why deep learning and why now? So one more thing. So when I'm conducting this session, I want this session to be a little interactive. So this is what I want to ask any one of you, any one of the participant, if they can, share their thoughts that why deep learning and why deep learning is boosting right now, like booming right now. It is like a big market right now. Do you have any idea like why it is such that deep learning is very, very, very booming? Anyone?
Now that most of the things are being digitalized, we have a lot of data which is being generated, and these techniques can be used to derive a lot of insights from that data, which can be helpful for business development and things.
Yeah, correct. So this is one of the aspects why deep learning is like booming right now. So let's see. Yeah. So if you see that neural networks or deep learning date back like decades and decades ago, okay. So why the resurgence or why the boom right now is basically, first of all, it has lots of, so currently in the, era of social networking and social media, we have like tons and tons of data. We have lots of terabytes of data moving on to the cloud, like floating onto the cloud, right? So one of the factor for deep learning or any kind of machine learning is we need lots and lots of data. Second thing, these data are easier to collect and store right now, given like there are multiple platforms like Google Cloud and Amazon AWS and all those stuff. So it is easier to collect, store data, and we also have social medias, and we have a lot of touch base with day-to-day network on the web, day-to-day interaction with the web. So that is why we have lots and lots of data. Okay, this is the first part. Second part, so earlier days, like 2 or 3 decades from now, like somewhere around in the end of 20th of century. Okay, so there were like very low level hardware. So there were no like high-end GPUs that we have right now, like Tesla and something else. So we don't have, we now have tensor chips because of Google. And yeah, there are lots and lots of parallel processing. Now we have M1 chip or M2 chip right now, Apple Silicon chip. So these kind of hardwares we did not have in earlier days, or like 2 to 3 decades ago. Okay. The third thing is like the software. Now the softwares are the software in the market for deep learning or else any kind of machine learning is too good, like TensorFlow, PyTorch, and all those things. So these are a few of the things. Look, these are the three major things. Because of that, deep learning is right now in boom, and it is practical. But if you see like if you see 50-70 years from now, in the year 1952, so the first thing that was developed was stochastic gradient descent. So I'll not go much into detail, but this is kind of something. So stochastic gradient descent is nothing but it is a regression technique wherein you try to come up with the predictions by the data which you have given. Okay, so in the year of 1952, we did not have this much amount of data or else hardware or software, any kind of things. Due to that, there was a dark day or else a blackout in the field of machine learning and deep learning, somewhere around from the year of 1990 to 2003 2004. Okay, then after that there was first machine learning activity that was happened, wherein a kind of a ImageNet ImageNet was developed. ImageNet algorithm was developed. From there on, there was a boom in deep learning, and more things were happening in that field, and that there was a lot of energy that was happening, lot of disturbances that were happening. There were a lot of activities started to happen from the year 2003 2004, and now we are here after somewhere around 15 to 20 years. Okay, wherein now we are able to do lots and lots of things with deep learning. Okay. So any questions till now, or should I move on ahead? Okay, cool. Okay, so for understanding what is deep learning, so for understanding the building blocks of neural networks, okay, so I will first go from A, B, C, D, but I'll not take too much time because we just have this 1 hour session. So first I'll move on to what makes neural networks or what makes deep learning, right? So let's first go to a very small unit of a neural network, that is perceptron. Okay, this is the structural building block of deep learning. So let's see what is a perceptron. Okay, so this is kind of the working or as the architecture behind a perceptron, wherein we have x1, x2 till a lot of variables. So these are nothing but different kinds of inputs. Okay, for example, if I give you example with related to data, so features are nothing so inputs have features, right? So for example, if you want to know the height and weight of a particular population, you have the entity name. For example, my name Karan, one column, which is just a nominal feature. Then we have weight column and we have height column, right? So these are nothing but height and weight are nothing but features or variables. So here x1, x2 till xn, these are different kinds of features which are taken as an input. Okay, these inputs, now there is you can say sum is happening, or else a linear operation is happening within these things, within this by taking these features as an input. So if you have seen something like y equals to ax plus b. Okay, so what is this operation? Do you know, guys, what is this operation? So this is a linear operation, right? Right, linear combination, right? So this operations happen where here, if we talk about x1, it is a x1 plus b. Okay, so in terms of this, so the a here is w. Okay, and there is something known as a bias. Okay, So this is what happens here in this particular operation, wherein this particular y is nothing but z here, okay, the intermediary variable. So some kind of linear operation happens. This linear operation goes ahead to another layer, or else goes ahead to other component or other operation. This is a non-linear operation, wherein this z which we get, this z is that converted into this z is applied, a linear or non-linear operation is applied on that z value, and then after this z value we get y. This is y cap, which is nothing but the prediction. Okay, so if you see y cap equals to g, I'll not go into this equation, but this is what the equation is, wherein we do some kind of linear operation, and this on this linear operation we apply some non-linearity, and we get the prediction as an output. Okay. Along with this, we also have something known as a bias. Okay, this is something known as a bias. One year, this is bias input. Okay, so what is bias? So any one of you who can, in a very layman's term or else a common term, can explain me what is bias?
Any deviation from the expected output.
Yeah, you can somewhat you're correct. Yeah, you are actually correct. So there can be, so data in real world, it is not it does not follow a normal distribution, right? So what is a normal distribution? It is a perfect distribution. Okay, so normal distribution is nothing but a perfect distribution. So this is what a normal distribution, wherein it follows mu1 and standard deviation as 0. Okay, so all the data in this world is not a perfect data. So to manage those kind of chaos, okay, so to manage those imperfection, we have bias term. Okay, so the bias term is taken into account that there can be some deviations in the data. So to take account some kind of deviations in data, we use the bias term, and we add it to the whole linear operation. Okay, so this is how a perceptron looks. Now this is just a single unit. Now what happens is we build up on this perceptron. We expand the structure of this perceptron. How do we expand the structure? Okay. This is how we expand the structure. So if you see, this is a multi-output perceptron. Now, what is multi-output perceptron? A single perceptron is now being so densely connected with each of the other outputs that it forms a multiple output perceptron, wherein if you see these variables from x1 till xm, it does not have a single output. It has multiple outputs, wherein multiple nodes or its multiple variables give an output of z1 and z2. So because all the inputs are densely connected to all the outputs, this is also known as a dense layer. Okay, so moving on to the multi-output perceptron. Now we make this thing more complicated, or else we expand the structure more. We add some more variables on some more things into the structure. Then we get what is a neural network. Okay, so that single layer perceptron now is converted into multiple output perceptron, and this multiple output perceptron then goes to the output variable. Okay, so this is how a single layer of neural network looks. Okay, which has a single hidden layer here. Okay, there's a single input layer and a single output layer. So this is nothing but a neural network from perceptron, from a single work of neural network or a single unit, we came into a whole layer and whole architecture of the single neural network. Okay, so if we moreover expand this neural network, what we'll do, we'll have multiple hidden layers here. Okay, we'll have 1, 2, 3, 4 types of hidden layers. So what happens is we then get deep neural network. Okay, so what do you mean by deep? So to deeply penetrate or to go into deep about the data and go into deep, or else you have multiple layers. When you have multiple layers or else multiple operations going on a single data, okay, a single unit of data or else a single type of data, then it comes to deep neural network, wherein we have a lot of layers over it. Okay, where if you see, we have the output, input, we have your output, and in between this, if you see these dotted lines, these are nothing but different hidden layers. So we can have 7, 8, 9, 10 hidden layers here, and the more layers you have, it is that the more accurate your results would be. But it is debatable, and there are a lot of things happening, a lot of things that we have to take into account, but I will not go in deep into that. But yeah, the more and more layers you have in your, or else the more and more layers you have in your architecture, or else in your algorithm, the more it is better for your network to perform, or else your algorithm to perform accurately. Okay, so we also talked about activation functions, right? So we also talked about some non-linearity. So non-linearity is nothing but there are activation functions which gives us takes into account the non-linearity of the data. So we already know how to do linear operations. It is so normal y equals to ax plus b. But how we calculate the non-linear part of the data? By taking into account some activation functions. So these are few of the activation functions. One of the thing is sigmoid and another one is ReLU. These are the most common activation functions which I'll talk about. You guys might have heard about these kind of functions, like if you have went through some of the papers, or else some of the articles related to deep learning or else neural network and all sorts of things. So let us see what is the difference between these two. So sigmoid there is a, so the difference between sigmoid and ReLU is, if you have to, if you have a binary zeros and ones, either your output is binary, a 0 or else 1, it is true or else false, then you always use a sigmoid activation function, then where it will give you kind of a thing between 0 and 1, kind of an output between either it is true or not. Then we go into ReLU. So ReLU is nothing but it gives you the value from 0 till infinity. But what about these things? So why the activation functions? Okay, so let me just go here. So the purpose of activation function is to introduce non-linearities in the network. So if you can see this graph, this is how your data looks, right? Okay, if you have a linear function, this is how the linear function will look at, wherein this particular line will fit in such a way that all the points, maximum number of points of this graph, of this graph, maximum number of data points should pass through that particular line. Okay, but this does not solve our problem. Okay, this does not give us a best fit. Why? Because it just takes into account the linear part of the data, this linear line, or is the straight line itself. What about these curves? What about these curves? How these curves we will take into account? These all curves. To take into account these curves, we have to add some kind of non-linearity, right? So activation functions enables us to use these kind of non-linearities, which can make our output more accurate. How? This is how it happens. If you see a simple linear function, this is how it fits a line, and this is how it classifies that the above the line everything is A, below the line everything is B. Okay, this is how it is categorized. But if you see here, whenever we add activation functions and we introduce non-linearity in our data, this is how we get the kind of the graph, or else this is how the line has been fitted, or else you can say the curve has been fitted over our data. So something which is in the red zone is A, categorized as A. Okay, and something which is in white zone, it is categorized as B. For example, something in the red zone is categorized as dog, and something in the white zone is categorized as cats. Okay, so this is in this way we can have our prediction more accurate, and we can also take into account the non-linearity of the data. This is why we use activation functions in neural networks. Any questions till now about deep neural networks? Do you want to ask something? Are you confused about what I was talking? Okay, cool. So I'll go ahead. So next, to understand YOLO, we understood what is a neural network. Now let us understand what is a convolution operation, or what is a CNN, or convolutional neural network. So here, YOLO is object detection algorithm. If we deal with object detection, we deal with images. If we deal with images, we deal with convolution neural network. So convolution neural network is nothing but the basis of image processing. Okay. So nowadays, if you know images, videos, and all those things, these things come in 4K resolution, right? So 4K resolution is in there. There are millions and millions of pixels in a single image, right? Or else a single stream of video. So these billion pixels, okay, work as parameters. Okay, for example, if you have 1 million image with 1 million pixel, then you have to deal with 1 million parameters. Okay, but right now it is not right now it is not that feasible. Okay, so it is not that we can streamline or we can run all this 1 million parameters at one go in our computer or else in our system. Okay, so to avoid this problem, or is this overcome this problem, what we do is we try to reduce these parameters. Okay, and along with that we also try to keep a lot of parameter or a lot of edges, a lot of features of our image in our prediction. How do we do this? We use convolution neural network. So what is convolution? If you see here, this is a image matrix. For example, I've placed in the background, I've placed a picture of a dog, right? So wherein you find an edge, you will see there is 1, and wherever there is no edge, you will see there is 0 somewhat. Okay, we also take into account some of the white colors in the images as well. So just think of it as an image matrix, wherein the image matrix is of a dog, a cartoon dog, which is facing towards us. And we have 1 wherein it has edges. We have 0 where it is full white, like full white. Okay, nothing else, not even a dot. So what do? We convert this image into this ones and zeros of the matrix. Now, if you see this particular thing, this is how you denote a convolution operation. Okay. This is a convolution operation. This is what a kernel is. So kernel can be anything. You can have your own custom kernel, or you can use kernels from the net where a lot of different researchers or authors have used their own custom kernels. So this is what a kernel I am going to use. Okay, so this is kind of a filter. So we apply this filter all over our image and we get some of the output out of it. Okay, so let's see what is that. So if you see, I am rolling over this particular, filter over the whole image one by one, and I'm getting this kind of input. Okay, wherein what I do is, if I am revolving this particular filter over this particular section, okay, so it is 1 into 1 plus 0 into 1 plus 1 into 1 plus 0 into 0 plus 1 into 1 plus 0 into 0. This gives me the value of 4. Okay, now I go ahead, I go to one stride next. One stride next means one step next. This is the first step I took. Now I'll take the next step. It is this one. Okay, now I'll convolve this particular filter over this particular step, and then I'll get the value 3, and I'll go on so on and so forth till I get this particular feature map. Okay, now you will see this 5 into 5 matrix is now converted into 3 into 3, right? So now it is 3 into 3. Now the number of features are also reduced, and the number of features are reduced. So it is easier for our computer or is for our machine to carry out operations in these less features rather than to going on and calculating the features of 5 into 5 or is calculating or operating on 5 into 5 matrix. Right. So due to this, we use convolution operations. We, convolve and we make we convert big images into small and operatable images in our machines. Okay. So this is how a convolution operation happens. Any questions over this?
Yes, I just wanted to ask one thing. How did we derive that filter through kernels, but on what basis? Because see, images will be all different kinds. So on what basis are those filters designed?
So there are various things that are taken into account. So there are various pre-built filters that we can use on our data. Okay. And there are also custom filters that we can use. So there is a lot of research happening over it. So there are 2 to 3 filters. I don't remember exactly the name, but they are something like some 2, 3, 4, some kind of a value, and they have a 3 into 3 filter inbuilt. So like if you go into TensorFlow, okay, so in TensorFlow, what you have to do, you have to just give them how many number of filters you want. Okay, and TensorFlow decides within what is its default filter. For example, it has a default filter of 101, 010, 101. This is what the default filter is. And if you want to override it, you have to go into that particular argument and you have to mention the filter name. So there are various filters out there. So I actually don't remember the name of the filters, but yeah, so you can decide on your own and
Okay,
see
so
the
we have to
output.
keep trying different filters and check what is giving the best result.
If you want to take that parameter into account, most normally we as a data scientist, we don't take filter as a parameter to take into account to increase the accuracy of our model. But yeah, if you want to go ahead and try it, you can do it.
And filters are usually these 3x3 matrices only, which would be used to calculate the convol feature.
Yeah, the common practice is to use a filter of 3x3.
Sure, thank you.
Okay. Any other questions, or should I move on ahead? Okay. Good. If I'm pronouncing the name right, Ishangi, right? It's good that you are asking questions. Like I'm not feeling like I'm talking to, I feel like I'm talking to computer when someone does not respond to me. Yeah. Okay. Yeah. Okay. Moving on ahead. So these convolution operation. Now what we do is, again, the same thing we did with Perceptron. We make it more complicated. Why? Because humans are complicated. Not like that, but yeah, we want to increase the accuracy. If you want to increase the accuracy, you have to make big and big architectures or big and big network. So what we do, we take this simple convolution network, we apply more layers and we expand the architecture. Okay, and this is how a convolution neural network looks. So if you see input, this input is nothing but an image. Now what happens is basically this image goes to convolution operation, and the size of this image reduces. Then it reduces again till whatever output, whatever kind of size we want. If we want size of 6 into 6, so we will just giving an example. If you want a 6x6 image, then 6x6 pixel image, then this is what you will get at the end of all the convolution. This is nothing but we have multiple convolution operations going on till we want a desired size of the image, which will work for operation in our computer. Okay. So then we go here, we put this particular output, we straighten this output, we put it into fully connected layer. This fully connected layer is nothing but the thing which we talked about. This neural network, this is also known as an FC layer. Okay, wherein this input that we see, okay, for example, the image is of an input like this, right? This is a matrix. The input would be in terms of matrix. Now what we do is we straighten this matrix. How we straighten it? we just unfold this matrix into a single vector or it's a single line. Okay, this is how it is, and this is how it happens. So this first pixel will go here, it will go here, this will go in x3, x4, x5, and xm. Okay, so this is how our input layer will look, and this operation is nothing but is known as flatten. Okay, wherein we just unfold the matrix, image matrix, into a straight vector, and we provide this as an input to our neural network, and this neural network is known as fully connected layer, as it is fully connected to the output. Okay, so this is how it happens. So this here, this network, this is an FC layer, fully connected layer, and then we have an output, whether it is a cat or it is a dog. Okay, so now you understood what is what is fully connected layer, what is deep neural network, what is convolution neural network. Now we have to move on ahead to, talk about what is YOLO. Okay, so YOLO is it's kind of a funky name. You only look once. So you only look once is nothing but so what YOLO algorithm does is it does not iterate too much. So a single image does not run through loop like multiple times. But when YOLO algorithm gets an image, it gives the prediction of that image in one go. Okay, so how does it how YOLO manage that? I'll just give a very basic knowledge about it. Okay, first of all, before going and understanding the working of YOLO, we'll just figure out what are the features of YOLO. Okay, so YOLO is you only look once. An image is passed to the YOLO algorithm only once, and it gives us the prediction. We don't have to again and again, iterate the image over that algorithm to get more and more accurate results. Okay, it's a real-time object detection algorithm. Just because it looks at a certain image or it's a certain video only once, or a certain frame. In terms of video, multiple images is a video, a single frame is an image, and multiple sets of this frame goes and converts into video. So it looks at a single frame or a single image just once, and it gives out prediction. That is why it is very much good for real-time detection. Okay, any versions of YOLO. So right now there is YOLOV5 that is going on, which is more enhanced than YOLOV3. So YOLOV3 is the third version of this algorithm. Okay, so this family of algorithm, it is very good for real-time object detection, and it can handle instances of mixed data. For example, if you have mixed data in your data frame, or else with you, okay, so mixed data as in you have video as well as images. Okay, so what you do, okay, you have to, sometimes it happens that you have an algorithm, you have to create a new different instance for dealing with video, you have to create this different instance for dealing with normal still images. But no, YOLO, if you teach, or else you make a YOLO algorithm, you construct a YOLO algorithm, you make the YOLO algorithm learn on your data, then you can also go and use the same algorithm or the same object to predict on images as well as predict on videos. You don't have to create any other new instances for it. Okay, or else change some kind of code, or else change the algorithm steps on it. Okay, so that is why it is very useful. Third, it makes use of only convolution layer. Now, this is something which is very different than all the algorithms right now. Okay, so in previous terms, I just displayed how a convolution neural network works. If you talk about faster RCNN or RCNN, this is how the structure of faster RCNN or else RCNN looks like, wherein we have a fully connected layer at the end to predict the outputs. But in terms of YOLO, we don't need that. It is a fully convolution layer, like it is constructed of fully convolution layer. It does not have a fully connected layer or else any kind of other layers. Everything is happening on convolution layer itself. Okay, being an FCN or being a fully convolution network, YOLO is invariant to the size of the input image. So you can pass somewhere around 4K resolution image to YOLO if you have constructed it in this way. And to the same YOLO algorithm, you can also you can also give 8K resolution images as well, or else 2K, or else just HD. So a single instance of YOLO or single YOLO algorithm can handle all the multiple size of input images. Okay. So in the right hand side, you can see I have just tried to explain you about what are features. Okay. So if you see picture of this cat, right? What happens is when you do convolution, okay, on this particular image, what happens is basically it takes the important features of this image only. For example, it does not take into account the texture of the fur in some cases. Okay, if you see in this case, it takes into account the edges, how the tail looks, how the ears look, how the mouth looks, are there any whiskers or not. Okay, these kind of things are taken into account. So the main important features are taken into account during a convolution operation, and it goes and moves on ahead into deep and deep into the layer. Okay, so you don't have to deal with this white background or else some other tree background or some other things that you don't need your algorithm to learn. Okay, so that is why it is very so these kind of convolution networks are very good to operate on images, higher end images or higher resolution images. Any questions till now? Should I move ahead?
Yeah, I'll ask. This is only the front side of the cat. So if we have the cat facing towards the side or a back picture of the cat, how is it like? Still, will it be able to identify that it is the same cat, or how is it?
Sure,
Because
that is
right
what,
now,
yeah, correct. Good question. So that is where image augmentation works. It is altogether a different concept. So what happens is basically, if you see a picture of this cat, what we do is we take multiple angles, okay, a picture of multiple angles of this cat. Also, what we do something known as zoom crop. Now, what we do, we split this particular cat image into, for example, if you want 4, then we like divided into 4 different pictures, and we just zoom it to the actual this particular image size. For example, if this is 16 by 16, we just crop it and zoom it so that we can learn multiple features. So what you do is basically you try to get those kind of data which is helpful for your algorithm to learn about the cat in any kind of circumstances. Okay, whether it is only in the half part of the picture, it is facing front, it is facing back, sideways, any other thing. So this is what you have to take into account when you are making your algorithm to learn. So if you use these kind of things, and if you use multiple kind of these images, and you have multiple angles and all those tricks that you have in your sleeves, then your algorithm will work very properly or else very accurately if you take this into account while making it learn.
so for my understanding, suppose we talk about the tail of the cat. So in
Right.
one picture, it's bent upwards, and
Right.
in one picture, another frame, it's falling downwards. And likewise, there are different frames.
Yes.
So if we zoom into that particular tail part of the cat, will it be able to identify and correlate that this is the tail, and hence these are the features for it likewise?
Of course. So what happens is basically, if we talk about, if you I showed you the perceptron, or I showed you the input layer, right? So for
Yes.
example, there is one node X1. It takes into account the tail. Okay.
Okay.
There is another input X2. This takes into account the ears. Okay. And X3 takes into account the whiskers. Okay. Now what happens is basically we we calculate this all the linear and non-linear operations over it. We calculate everything and we come up with a value between 0 and 1. Okay, if we, for example, if this is 0.2, the value of x1 is 0.2, value of x2 is 0.3. It means that he's he's 20% sure that this is a tail. He's 30% sure that this is a ear, and he's like 50% sure that the algorithm has seen whisker. So if we add all this up, we get 0.9. Okay. So 0.9 means the algorithm predicts that 90% this is a cat.
So it
now
adds up for all the accuracy percentage, it adds up and then tells that it is 90%.
Adding up, I've just given you an example, but there are a lot of different.
I think there would be average out or something.
Yeah, there are weightage also. There is optimization. There is gradient descent that is happening. There are a lot of things that is happening in the background. But to explain you, this is what I feel it is very easy for you to understand right now. That what is this is what happens, kind of a basic understanding. So so this way it can measure that it is 90% sure that this particular thing is a cat. So now you give any kind of angle to it once, but there is a condition. You first have to make your algorithm learn on millions of cat pictures. Okay.
Yes, but those pictures can be different, right?
Yes,
taken from different angles.
Yes, different angles. Correct.
But can you go back to that slide where you were talking about that convolute feature, that bigger matrix was shrunken down to a smaller one?
Yeah, correct.
So like if we talk about this image matrix, in this, say in one picture, the dog's tongue is out, and in the another picture, the dog tongue is not out. So here in the image matrix, it will be 1 for the picture 1, and for the second picture, it will be 0.
Correct.
Because there is nothing in that.
Correct.
But here, finally, when we calculate from the image, we calculate the convolute feature, there the numbers will come different. Say it will come 3 for one and 5 for the another one, because according to 0 and 1, it's calculating, taking the filter.
Correct.
So then how will it identify that this particular, from the convolute feature only, it is convolute feature only, it is identifying that this particular is the input for the tongue. Right, because this gets flattened up and goes as an input for your CNN.
Right.
So then how will it identify that this particular block, say the third column and the second row is the block for calculating the tongue?
Right. So
how does it understand
there is something known as weights, right? So
yes.
I showed you W1 if I've missed. So if you see here, so there are these weightages. Okay.
Yes.
So weightage is nothing but the priority given to this particular feature. Okay. So for example, X2 is responsible to detect the tongue of the dog. Okay. But it has a weightage of only 0.01. Okay. Now you tell me, will it take into account in the later part?
No, it will not.
Why? Because we have supplied the images of dogs with tongue out. The supply is only kind of somewhere around 1% of the whole data set where the dog's tongue is out.
Okay.
Okay. If this is just an assumption or just an example I'm giving you. If, for example, you have 100 images of dogs, and out of those 100 images, you have 10 images of the dogs with tongue out. So this weightage will convert from 0.1 to 1.0. Right. So now next time when your algorithm will try to predict an image, it will have a 10% of weightage that it should also detect the tongue.
Okay. Otherwise, that weightage is given to some other feature, to the next feature.
Right.
Okay.
That is why we have your W0, W1, W2 till WM. This defines whether this particular feature is how much important in our neural network.
Okay.
Good questions, by the way.
Thank you.
Yeah. Okay. So we discussed about the features. Now let us see what is the architecture. Okay. So for example, this is 608 by 608 pixels of image. Okay. So what happens is basically it goes under lots of convolution layers. like multiple convolution layers. And what happens is there are some connections wherein there happens a skip, and the outputs are concatenated. So for example, if you see here, the first layer here, okay, so there is one result which is coming out of this. Okay, so what happens is this 608 by 608, it convolves into 76 by 76. This is how at this particular step. Okay, now what happens is now a prediction happens at this particular step. Okay, or else a line is trying to get fit, or else a curve is trying to get fit on the image to recognize that particular entity like dog. Okay, now this result is stored. Okay, now this result is stored. Now again there happens more convolution again in the network. Okay, now this comes to 38 by 38, your original 608 by 608 image. It convolves, and the size decreases, and it comes to 38 by 38. And again one more prediction is happening over here. Okay, now that prediction again is stored. Okay, now next what happens is basically it convolves more and more, and now we have 19 into 19 by 19 by 19 pixel of image after convolving, and then it takes prediction out of this image as well. Now what happens is all these predictions are not then concatenated, or as you can say summed up, and the actual prediction happens. So why you only look once, and why this architecture is basically in a single go. This algorithm tries to predict on a single image 3 times, so that it is more sure that whatever it is predicting, it is accurate or correct. That is why it goes only once, and we don't have to iterate the image again and again. And that is why it is used in real-time detection. So there are a lot of things like skip connections and YOLO detection block. I'll not go much into that detail because now I have to take altogether a deep learning lecture over here. But yeah, this is the common basic operation that happens where at certain point of time, or a certain point of algorithm cycle, their image is split out, and then the detection happens on the prediction happens on the image, and then it is stored. Some values are stored, and at the end all the values are concatenated and a result comes out. Okay, Ishangi, any question?
No.
Okay, so let's see what is basic idea behind it. What is basic idea behind this operation that I talked about? Okay, so the basic idea is it runs convolution operation on images with 3 different depths. Okay, these 76 by 76, 38 by 38, 9, this is nothing but the image depth. Okay, so what it does is every time it runs convolution operation in 3 different image depths. Okay, that is why it is just you only look once, and on one go prediction happens. Then the convolution operation divides images into grids. Okay, if you see here, these images are divided into grids. Why it is divided into grids? Because if you know about the golden ratio, anybody, if you take an image, okay, this is the golden ratio. If you take an image, if you keep the subject at this intersection points, then your image comes very properly, or else your image is captured beautifully. Okay, so to get more and more features out of images, these particular images are then split up into grids. Okay, and convolution operations happen within these grids. And there are a lot of other things known as anchors and something else, which I'll not talk about because it is very confusing. Okay, so just you have to keep this in mind that YOLO divides this images into grids, and this convolution operations happens on this grid. Why this grid? So that if for example, if you have taken this particular grid which is in red, so you can say that this grid is responsible for the detection of this whole dog, as this is the you can say the main grid. Okay, or is the center grid of this particular object. Okay, so how can we do this? we can only know, we can only detect properly if we, split it into grids and we use these grids as notations, okay, or else a path for the detection. Okay, if you use some kind of path for detection, or else some kind of, areas, or else some kind of notations for detection, then your detection is more accurate and more faster. Okay, so 3 different grid images are created from one single image, like 3 different depths. These 3 different depth images have 3 different grids, and it is generated from one single image. Each of this image runs through a YOLO detection block, as I mentioned in the earlier slide. And then the 3 outputs are concatenated together to predict a single prediction output. So this is the basic idea of YOLO. Okay, any questions over it?
Yeah, the size of these images, the grids which will be formed would vary from image to image depending on our input image size.
Correct. So there are something known as YOLO detection block, wherein you can give yourself, if you want your image into 13 into 13 grid, if you want your image into 256 into 256 grid, you can, you can change those parameters as well.
Okay. Otherwise, the algorithm takes on its own.
Yes, correct.
And I am sure it's definitely advisable to go for a bigger, more grids, bigger image size.
Yes, correct. So more the grid that your image has, the
Better
more
accuracy.
real estate area it can cover. The more real estate area it can cover, and this anchor, anchor, this is what is an anchor, the detection part, the particular grid which detects the whole object. Okay, the smaller it is, the more accurate it can detect a particular object. But yeah, but the smaller, then if it becomes too small, then it can also detect some, jargon things, or else a single leaf out of a
because then it will not be able to differentiate.
Yes. So you have to, keep in mind these all things. You have to take something which is known as an optimum value for all of these things.
And is there a way to find that optimum value? Like,
you have to try and test it out.
It comes by experience.
Yeah, it comes by experience, and it comes by running the algorithm again and again, or is making some kind of change. First going through testing it, how is the accuracy, then going back again. If the accuracy is not correct, then let's do one thing, let's increase the data size. Then again the accuracy falls down, it means there is no issue in the data size, you have to increase the network size, so on and so forth.
Okay.
Okay, now I'll talk about use case. I'll not take much time. I guess it is, it is over the time, I guess, like 2 minutes. But yeah, I'll just quickly talk about the use case which I have. So this is what I have done in my last project. So that I was working on, and we delivered this project. So this is a use case wherein we had to detect antennas on mobile towers. Okay, so basically, why we used YOLO and what was the use case. So there is a big giant European operator, okay, mobile network operator, okay, somewhere around, if here the giant operator, mobile operator is Geo, okay, so somewhere around Geo of European countries, okay, they came to us and they wanted something known as, so they wanted to use artificial intelligence to detect components, or else to detect antennas on their mobile towers for inventory management. Okay, so for inventory management, as in at the time when they installed the tower, they drew an Excel sheet. Okay, in that Excel sheet they placed, they jotted down all the components they placed on those towers. Okay, so for example, I placed these particular kinds of 5 antennas of this particular kind, 5 antennas of kind B, and 5 antennas of kind C. So they already drew out these Excel sheets. Now what we wanted to do is, after they installed this mobile tower, 6 years, 8 years passed on. Okay, now they want to inventory manage. They want to check whether whatever things they have installed and they have jotted down, is it true or not. Okay, if it is true, how the equipments are, and like all the equipments are in good condition or not. Okay, whether some of the equipments are rusted, then we have to replace those equipments. So these kind of, you know, inventory management and maintenance kind of thing was a use case wherein we had to chip in with help of AI. Okay, so object is to detect multiple network components in tower image and do inventory management and maintenance. Okay, maintenance as in we have to check whether the components have rust or it is in good condition, whether it is broken or not. Okay, so the data here consisted of a mixture of site images. So site images are nothing but the tower where all of these things are is known as a site. Okay, right? So a tower site. So we had multiple images of this tower site. Okay, multiple tower images and everything, and we also had drone videos. Okay, so now recall, why did we use YOLO here? Right, we use YOLO because we had a mixture of data and had a mixture of images and videos in our data. Okay, so it is a multi-detection use case. Okay, and if it is multi-detection use case, YOLO is always a go because it uses the grid structure wherein we can, you know, detect minute particles, components. For example, if you see this tower image, will you be able to detect how many components or how many kinds of antennas are there? No. Why? Because it is very minute. Okay, when we have to detect minute things, we have to use some kind of grid triad structure which YOLO offers. Okay, and also it is one of the best object detection algorithm right now in the market. This is why we went with YOLO in our detection, in our use case. Okay. So we took YOLO. We took YOLO as an algorithm. We made the architecture. We took the data. We annotated the data. We did a lot of things. Okay. Then we ran the algorithm, but our accuracy was not that good enough. Okay. There was something which were missing. Okay. Accuracy was not good, and also there were, if you see this yellow box over here, so this is a detection box where it is detecting that this is a particular kind of antenna. But what was happening in our case was we were having 8 to 10 boxes on a single object. Okay, which was hampering with our accuracy. Abhi 7 8 boxes will detect the same object, then it is very tough for us and for us to understand, or also for the output. Okay, so for this single component, if there are 7 detection, it means that there are 7 objects, which is not correct, that there is only one component. But but our algorithm was detecting 8 components on this particular space itself. So how did we, you know, overcome this problem? Okay. Okay, so first of all, the first thing was the intersection over union. So intersection over union is nothing but an evaluation matrix. Okay, what it does is basically, when we tag those images, when we draw a bounding box and we say the algorithm that this is a stop sign. Okay, so that is what a ground truth box is, and the red box which we see here, this is what our algorithm predicted. Okay, now what we do is we try to calculate this intersection over union. How? It means the area of overlap, like how much of the area is getting overlapped. So if you see this particular box that I'm drawing, this is how much the area is overlapping. Okay, over the area of union. Okay, the total area. So if this particular percentage is higher, for example 85%, then our algorithm is good. And if it is not high, so here if you see the IOU is 92%, so it is an excellent detection or else excellent prediction. Okay, so this way we try to evaluate it. So if this is excellent, then it is good. If it is not excellent, then run our algorithm, do some parameterized changes, do a lot of things, and then come back and see if whether we come to an excellent mark or else at least a good mark. Okay, This is one of the things that we tried to improve. Okay. Another thing was non-max suppression. Okay. So whatever we talked about, right? So one particular component were having 7-8 bounding boxes, right? So what we did is basically we tried to merge these bounding boxes into one single green bounding box. How did we do it? We tried to get a ground truth box. We tried to get our ground truth box that we talked about, this particular green box, and we tried to see whether in this particular green box how many boxes were getting generated after prediction. Here, if you see, there is only one box. Okay, so it is good. It is fine. It is a good prediction. But for example, if this red box is placed 6 or 7 times in with along with this green box, that is ground truth box, then what we do is basically the box which has the most area close to the green box, we only take that box into account, and that only one box, and that ensures that we only have one detection for one component. So this is how we, improve the accuracy. So Ishangi, this is Ishangi and everyone. I guess Ishangi is only talking, so I am talking back to her. But this is how we improve the accuracy, not just by the increasing the filter, decreasing the filter, or else getting more images and all those things, but using these sub algorithms as well for making it more accurate. Okay. So I'll quickly talk about the approach. So our approach was we get an input of image and video. Now what we do is we pass this input to an image sorting algorithm, wherein it will sort whether it is a mobile tower. It is just a shelter. Shelter is nothing but a battery house that is situated along the tower, or else it is a rooftop tower. Now once the image is sorted, now we run our YOLOV3 algorithm and we try to detect different kinds of antenna, whether it is a panel antenna, parabola antenna, dish antenna, and all those stuff. And then we place all of these things into an Excel file and we try to automate the inventory check, whether everything is proper or not. And then we then we print a result wherein everything is proper and the inventory is good to go, or if some issues are there or some things are rusted, we have to replace those things. All of these things comes into the results. Okay, and this is how a YOLO video output looks, wherein if you can see, it is kind of a real-time detection where it is taking the output from a security camera on a highway, and it is continuously detecting the cars that are running at a particular given time. Thank you. This is what it was about.
Hi, Karan, Nida here. Karan, you can share with the participants approximately on how many images had you trained your model, or how many images had you got as an input before you went for the further process?
Okay, so we had to train. So we got an image of somewhere around 26,000, which was not that enough at the first go. So what we did is we built up a vanilla algorithm. Vanilla algorithm is kind of a starter algorithm wherein it will it is kind of a benchmark. Okay, so now we ran the algorithm with 26,000 images. We got an accuracy of somewhere around 50 to 58%. Okay. So this is kind of a benchmark. Now we have to increase the accuracy over it. So what we did is we went back to the client. We asked them to give me at least 1 lakh images. Okay. So we took 1 lakh images. We hand engineered those images. We then did image augmentation over it. And we came back with somewhere around 12. We had 12 augmentation over a single image, and then we got somewhere around 8 or 10 lakh images, and then we ran our actual algorithm on those 8 and 10 lakh images, and then we got an accuracy of somewhere around 86% right now. The detection and the classification somewhere around 88 or something like that. So both of the things, the detection accuracy and the classification accuracy, both of the things were somewhere around 80s and 85.
Okay, great. Participants, do we have any questions?
Oh, yeah. Can you go back to that slide where you showed the cars running on the highway? So what is it actually detecting? The car and their registration number?
No, no, no. So basically, there are two types of detections that are happening here. So the first detection is detecting any object. Okay, any object, as in any moving object, which looks similar to our classes. Our classes is nothing but, for example, if you want to detect cars, we'll have different classes. That it is Audi, it is BMW, it is it is any other car, it is Tata Nexon or something like that. Okay, this is the first. These are the classes. So what it is doing is it is first detecting the car. Okay, it is printing the accuracy, and then in other part it is not over here. Then after that there is something known as classification accuracy that I talked about, right? So once the car is detected, it will detect whether it is a Nexon, it is Audi, or it is BMW. So that is classification accuracy. So right
Okay.
now it is just it is giving us the detection accuracy, whether the car object is detected or not.
Okay, so if on the highway some like something else is also running, say a motorbike or a truck, will it be able to
No, it will
tell
not
that?
detect unless and
Only the
until.
cars which are
Yes.
running will be detected and the
Yes.
classes of those cars.
Yes. If you have trained your algorithm on car images, then it will only detect car, not deer, not elephant, not motorcycle, nothing.
Participants, do we have any questions? All right, then I guess Ishangi, do you have any question?
No, I just wanted to ask how many images he took for that car detection, because I'm sure it'll be front facing, back facing, different cars, multiple lakhs, maybe millions.
Yeah, I just give you the number of the actual use case that I've done, somewhere around 8 to 10 lakhs images to detect those network components. So yeah, it needs lots and lots of data, and that is why AI is booming right now, because you have very much like tremendous amount of data right now with you, which was not the case in 1950s or 20th century, basically.
All right. I guess we come to the end of the session. Thank you, Karan, for having a wonderful session. And I guess the highlight was the case study that you took up, wherein you've actually worked on a case study which uses a deep learning model, wherein most of the companies are still working on the classical ML models.
Yeah.
You did give an insight about how a deep learning is being used in the industry. That's why I asked you the number of images, because to give the idea to the participants that when you're working on a deep learning model, how like the size of the data has to be enormous, otherwise it doesn't work well on small amount of data. So
Yeah.
thank you once again on behalf of Aegis School of Data Science. Thank you for coming here and sharing your valuable experience and giving your time to all the participants.
Yeah.
Thank you once again.
Thank you very much, Nina. Thank you, everyone.
Thank you, guys. Have a lovely evening.